Okay, so we have done some simulation in the last class where you have a dielectric boundary. On the right hand side, you send the wave, then you see that some of the wave is reflected, some of the wave is transmitted. So now the amount of transmitted wave and reflected wave are given by your reflection coefficient and the transmission coefficient, and we have calculated that when we have a free space epsilon 1 relative permittivity is 1 for free space, and if we have a dielectric of epsilon r2 is equal to 4, then gamma is turns out to be minus 1 by t and tau turns out to be 2 by 3. And we have seen that wave, as soon as it enters the dielectric region, amplitude has been reduced to 2 by 3, and some of the wave is reflected and it's a negative sign, so the wave is inverted and the amplitude is 1 by 3. We have seen that. So now today what we're going to observe is that when I have a boundary, whenever the wave hits a boundary, there's a reflection coming out from that. So we want to have no reflection from the boundary. So there's a simple boundary condition here. We'll see later on there is some advanced boundary condition which is called perfectly matched layer. This is a simple absorbing boundary conditions. At the boundary, you absorb the wave so that there won't be any kind of reflection. If any of the wave is reflected from the boundary, it's going to interfere with the wave which is propagating. So how do I do that? So if you just remember, if I want to find electric field, I need to have a value of magnetic field in the surrounding. And if I want to find magnetic field, I need to know the electric field in the surrounding. So, but then at the edge of the problem, at the end of the problem, at the end of the solution space, will not have any fill outside the solution space because there are no sources outside the problem space. So our problem solution space is fixed. Beyond that, we don't have to observe the waves. So we don't have to observe the fills. There's no fills outside the solution space. And we also know that we have, according to the current stability criteria, delta z by 2 is the distance the wave move in one time step. We have intentionally chosen that. So that there should not be any kind of divergence of the wave. We should not have unstable solution space. So our wave is moving at distance of delta z by 2 because of the current stability criteria we have assumed in one time step. So it takes two time steps for a wave front to cross one cell. So one cell is of delta z, but over a time instant delta t, wave is moving a distance of delta z by 2. So wave requires two time steps to cross one step size, delta z step size. And we are at the, let's say there are two boundaries. Let's say if we have running index for the k is going from 1 to capital N, one boundary is at k is equal to 1 and one boundary is at k is equal to capital N. So let's say if I actually consider the left side boundary where we have k is equal to 1 and electric field at k is equal to 1 at one particular instant of time is Ex 1 comma n. 1 means we are at the k is equal to 1, n is the nth time instant. And somehow I force the electric field at the next discretization element, that is k is equal to 2, Ex at 2 at n minus 2. So you know that waves need at least 2 delta t to move at distance of delta z. So this and this, how much is the difference in the distance? This is at k is equal to 1, this is at k is equal to 2. Distance between those two is 1 delta z. And wave requires 2 time instant to move this distance of delta z because of the current stability criteria. So if we force the Ex at 2, which was the wave at n minus 2, it will reach the Ex at 1 at n. If we make them equal, there won't be any kind of reflection. This is the changes we have to do at the program so that we don't have any reflection at the edges. You can do it similarly for the k is equal to capital N also. We'll do some simulation and see when I put this condition in program, there is no reflection at the boundary. Later on after I finish this lecture. Okay, so 1D Fdtd is done. So we'll go to the 2D Fdtd. In the 2D Fdtd, there are usually people usually solve it for two cases. One is for transverse magnetic and this is for transverse electric. And the notation is TMZ. TMZ means magnetic field is perpendicular to the Z direction. TEZ means electric field is perpendicular to the Z direction. If magnetic field is perpendicular to the Z direction, then magnetic field will not have any Z component. Magnetic field is not having any Z component, then it can have component X and Y. And electric field is perpendicular to the magnetic field, so electric field will have only EZ component. For TZ mode, basically electric field is perpendicular to the Z direction, so electric field will not have any Z component, so it will have only EX and EY. And magnetic field is perpendicular to electric field, magnetic field will have only Z component. So we have only 3 components of the field. Usually we have 6 components of the fields, because electric field is a vector, it has 3 components, magnetic field is a vector, it has 3 components. If you solve it for TMZ and TZ case, you get only 3 components of the field. And there's a major difference here. The confusion is that in your waveguide analysis or any kind of EM analysis, there is a wave propagation along the Z direction. So let's say you consider rectangular waveguide or circular waveguide, wave is propagating along the Z direction, and you don't have any, for the TZ component, you don't have any component of the electric field along the direction of propagation. But here, it's a 2D Fdtd simulation. Everything is confined in 2D plane. So we don't have any wave propagation along the Z-axis. That's a major difference you have here. When I do the simulation, I actually assume that wave is confined in XY plane. There will be propagation along X and Y direction, but you will not have any propagation along the Z-axis. So this is a 2D Fdtd simulation, which is completely different from your waveguide analysis, where you have wave propagation along Z-axis. If you have TZ, then you say that electric field doesn't have any component along the Z-axis, but wave is still propagating along the Z-axis. So here it's not like that. Wave is confined in XY plane, is propagating along XY directions, but it doesn't have any propagation along Z-axis. So now, because of that, if I don't have wave propagation along the Z-axis, del by del Z would become equal to 0. And if you consider TMZ case, IZ is 0, IZ is 0, TMZ, it doesn't have any component on the Z-axis. And magnetic field will have Hx and Hy, and electric field will have only Ez, so Ex and Ey is 0. If you put this condition in the 6 Maxwell equations, components of the 2 Maxwell equations with 6 scalar Maxwell equations, let's put that condition. Ey is 0, Ey is 0, Ex is 0, then Hz is 0, Ex is 0. Then we can simplify the 6 equations into just 3 equations here. 3 equations with a very much simplified version of the Maxwell equations when you consider the 2D Fdtd analysis. These are the 3 equations we'll be discretizing in both space and time to get the Fdtd update equations. So here, just like in the 1D case, I have shown you one diagram where you calculate Ex at n minus half, then Hy at n, Ex at n plus half. How do I calculate Ex at n plus 5, n plus half? Based on the value of Hy at n and Ex at n minus half. That diagram is the most important part of Fdtd for 1D case. Just like that, there is a diagram you need to understand and remember for the 2D Fdtd case if you want to write the program properly, if you want to understand it properly. I call it, this is the master diagram for the 2D Fdtd. Whatever diagram I have shown you, discussed today in the slide number 17, that's the master diagram for 1D Fdtd. If you know that diagram, you can write your Fdtd program, you can understand your Fdtd program properly. Similarly here in this slide number 45, this diagram is a master diagram for the 2D Fdtd. If you know this, you can write your Fdtd code, you can write your Fdtd update equation. So let us try to understand this diagram. Electric field is here at the center, magnetic field is circulating the electric field along this direction. So now you look at the electric field. Electric field, we are considering TMZ case. Electric field has only Z component, Ez, and we are calculating electric field at integer space steps I and j. I is the running variable for the X component, and j is the running variable for the Y component. That means this should actually be I delta X. This should be j delta Y, but we just write in a very short form. So electric field is calculated at the integer space step I and j. Since I have calculated electric field at the integer space steps, electric field is coming out of this surface. This point here means electric field is pointing out of this surface. So if you move a distance down here, y is going to, this is y-axis, this is x-axis. When I move down here, y has changed. So this is your x direction. X means x is having field along the x direction, So this is the vector which is pointing along the x direction, x. And when I move a distance down here, y has been changed. So y variable is this. So y will become j minus half delta y. So I still remains the same. We are at the same location along the x-axis. Only the y is changed. So if you go up, then x is still the same I. Then this is actually j plus half delta y. So it has moved up. So how much it has moved up is j plus half. You move this side, you have moved along the x-axis. So I will become I plus delta half. And this is I y. So it will be pointing along the y direction. J doesn't change because we are at the same level here. Similarly, if I move a distance along this direction, we are still in the same level along the y direction, but we have moved a distance of I minus half delta x. So I minus half I minus half delta x, j delta y. So if you just remember this formula, you can write the FDTD update equations, FDTD code very easily for 2D FDTD programs. So electric fields are calculated. This is what you need to remember when you write the update equation. Electric fields are calculated at integer space steps, and electric fields are calculated at half integer time steps. There are two steps, one for the space, one for the time. So we have seen that from the previous master diagram for 2D FDTD, integer space steps we have, but time would be half integer time steps for the electric field. Magnetic fields are calculated at half integer space step and integer half integer space step and integer space step. You have both I and j. One of them would be half integer space step, another will be integer space step. And magnetic field will be calculated at integer time steps. That's all. You will have terms like this here. What are these terms? Let's look at it. For example, if you have y, then this would be at the integer space step, but the remaining variable I minus half. If you have x, this would be integer space step, the remaining variable is j minus half. You will have terms like this in the FDTD equation. Again, here y, then j, then this is I plus half. Then x, then I is the running variable for x, and it will be integer if you have an x here. That's how you can remember. So let us go back to the central finite difference approximation of the first equation. This was the first equation, FDTD equation for 2D FDTD. Dou z by dou t is equal to 1 by epsilon dou xy by xx minus dou xx by dou y. So now this time derivative, so time derivative, what is the running variable for time? It is a partial derivative, so we will do only differentiation with respect to time, partial derivative with respect to time, Ez at n plus half and minus half divided by delta t. What was the location for Ez? Ez was ij, n plus half and minus half divided by delta t. And look at this term here in the right hand side, first term here. Let us look at it. Xy, this is a partial derivative of xy with respect to x. You have a delta x here. And we know that time running would be half integer time step, so I plus half. Time running index is n, and so this is integer here. Partial derivative with respect to x, so you'll have I plus half, I minus half here, j and j. Since we have y here, this would be an integer here, y and j, so I plus half, I minus half. You are doing partial derivative of x with respect to y, so x, then x and corresponding running variable is I here, so x, I, partial derivative with respect to y, so j plus half, j minus half. Time would be integer time step n here. Let us look at the second equation you have for FDD update equation you have here is del Ix by del t minus 1 by mu del Az by del y. So now Ix here you are doing time derivative, so n plus 1 and n. Magnetic field is calculated at integer time steps. So you have n plus 1 here, n here, it's integer time steps. And Ix, then this should be I here. Then you will have j plus half here. Similarly, Ez by Ey, Ez is always calculated at the integer space step. So I, delta y, because you are doing partial derivative with respect to y, del by del y, so j plus 1, g. And integer, half integer time step, so n plus half, n plus half. That's how you do the second finite difference approximation of the central finite difference approximation of the second equation. Let's look at the third equation. So del Iy by del t is equal to 1 by mu del Ez by del x. So this is a partial derivative with respect to time of Xy, then this should be J here because y and j are the corresponding running index. We do partial derivative with respect to time, so it will be at the half integer time steps. So I plus half is the you actually do partial derivative with respect to time, and the magnetic fields are calculated at the integer time step, so n plus half and n. And since I already have Xy J here, I should have I plus half here. Look at the right hand side, electric field is calculated at the integer space step and half integer time steps. So n plus half, and partial derivative with respect to x, so I plus 1 I, j remains the same divided by delta x. So you can rearrange the term, like if you want to get the update equation, you just keep on the left hand side the latest time instant electric field and transfer the previous time instant electric field in the right hand side like you have done for the 1D Fdtd case, and you simplify it. This is what you have the update equation. You can also have the magnetic field update equation like this. Ix at the latest time instant equal to Ix at the previous time instant, and so on. Xy also, Xy at the end n plus 1 times 10 is equal to Xy at n times 10, and you need to find out the electric field of the neighboring cells. So if you want to write the computer update equation, you cannot have this half here. So n plus half and n minus half, this you put it in a loop. If you put it in a loop, then automatically this time loop, you put in a time loop, then if you calculate Ez at n plus half is equal to Ez at minus half, it will be automatically taken care of. So Ez and Ij is equal to Ez and Ij. So all the half terms like I plus half, I minus half will be replaced by I minus half, because I minus 1, because we cannot have any array running index is half integers. So with I plus half should be replaced by I, and I minus half should be replaced by I minus 1. So this same equation you can write a computer update equation here, so like this. Similarly, you can also write the computer update equation for this Fdtd update equation by replacing j plus half by j, and mu r is usually 1 if you consider it's a non-magnetic materials or dielectric material. This is the equation for magnetic field. Similarly, you can also write the update equation for Xy, replace I plus half by I and mu r by 1, then you can simply write this the computer code. Okay, so one more thing is that how do I observe the wave? So it's a wave now in the 2D plane. In the 1D plane, it was a, let's say if I'm sending a Gaussian pulse, I just see the Gaussian waveform moving towards the right side or left side. If I place the Gaussian pulse at the initially at center, then it was moving towards right and left. But here, it's not like that. So it's a 2D wave. 2D wave you want to see. You want to know how is the field behavior in 2D plane. So now you have to use different commands here. Commands especially used here is called image command. Image C. C is the matrix. Image matrix. Depending on what values this C has, you can observe the image of the field in real time. And you can also have image scale. Image scale is you want to see which color is giving you the maximum color. For example, red is the maximum field. those you want to display on your Fdtd simulation, you can so you can scale the image first, then you can show the color bar. Color bar will show which color is giving the maximum fill, which color is giving the minimum fill. You can have color map, and in this C matrix, every row is a color. You'll specify in terms of RGB. R is the first one, second is the G, and another is RGB. You usually do it, no? If you want to do image processing or you want to do some kind of drawing, then you always specify all colors in terms of primary colors, red, green, and blue. So RGB, red, green, and so color intensity can be in the range of 0 to 1. If you could give different values of RGB, you can generate different colors. For example, 00 is black, 11 is white, 100 is red, 0.5 is gray. So 127 by 255, 1212 is aquamarine. So different color will have different values of the RGB. You can, okay. So this would be your Fdtd programming exercise 5 or 6. Let's see. Maybe you have skipped Fdtd programming exercise 5. Then, okay, we'll discuss that later on. I think I have skipped Fdtd programming exercise 5, which must be of the absorbing boundary condition. So I'll discuss it later on after I finish this recording. So let's look at the Fdtd programming exercise 6. So I'll show you Fdtd programming for TM case, and I'll show you the video in real time. Then, for example, that program is for the free space. If I have a source at the origin and if it is sending out signal in all directions, how is the wave behavior? So that program I'm going to show is for the free space. But let's say if you have a dielectric layer in the right hand side, like you have done for 1D case, if I have dielectric layer, what happens to the wave when it hits the dielectric layer? That you have to do as a program exercise. So you have to modify the program. So if you have done the Fdtd program for 2D, Fdtd program for TM case, if you want to just modify it for dielectric case, all you have to do is at that location ID and JD, at some specific location, you have to just specify the value of epsilon r. Epsilon r, let's say we take it 10. And because of this epsilon r, you can see that the constant C1 is going to change. And if you just make that small modification in the assignment of the medium or the location of this dielectric space by just changing the value of epsilon r from 1 to 10, then you can run the program freely. You can see how is the reflection and transmission of the wave at the interface. And you'll see that whenever you have a medium of higher dielectric constant, wave will slow down and pulse will also become shorter. You can also do the Fdtd simulation for TM wave propagation due to multiple sources. Instead of having one source, if I have an antenna array, if I have 7 or 8 of them, how is the wave propagation? We will show you that simulation after I finish this presentation today. Okay, how much time do I have? I do not have much time. Okay, we'll run up here.